A server with 100 concurrent editors was killed every 30 minutes. The culprit wasn't a memory leak. It was the operation history buffer storing every single operation since session start, never compacted. After 30 minutes, 900K operations consumed 3.6 GB of RAM. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover design Google Docs. Google Docs is a system that lets multiple users edit a document at the same time. The core challenge is handling concurrent edits without data loss. The solution is operational transformation, or OT, which transforms each operation against concurrent ones so all clients converge. Without OT, concurrent edits can cause data corruption. For example, if Alice inserts A at position 0 and Bob inserts B at position 0, a simple merge might produce AB or BA but lose intent. OT transforms operations so they apply correctly regardless of order. Here's a simplified OT transform function for insert operations. It adjusts the position of one operation based on the other, using a tiebreaker for same positions. This ensures both operations can be applied in any order and produce the same final state. Google Docs uses a central server that sequences all operations. Each operation gets a monotonically increasing version number. The server transforms incoming operations against the history and broadcasts the transformed version to all clients, guaranteeing total order. The server receives a client operation with the client's last known version. It transforms the operation against all operations after that version, applies it, assigns a new version, persists it, and broadcasts. This ensures all clients see operations in the same order. When two users edit the same word, OT transforms both operations. But edge cases like deleting a range that someone inserts into require careful handling. Google Docs uses character IDs instead of positions to avoid the shifting index problem. By assigning each character a unique ID, operations reference characters by ID rather than position. This simplifies transformation because you don't need to adjust positions. If a referenced character is deleted, the operation becomes a no-op or is transformed. Showing remote cursors is hard. Each client broadcasts its cursor position as a character ID. The server must transform cursor positions against operations. If the anchor character is deleted, the cursor moves to the next valid character. Throttle updates to avoid flooding. This function transforms a cursor when an operation deletes its anchor character. It finds the next valid character and updates the anchor. Without this, cursors would float in the wrong place or end up outside the document. The server must persist every operation before broadcasting to survive crashes. A write-ahead log with a sync flush avoids latency spikes. On recovery, replay the WAL to reconstruct document state. Clients acknowledge operations to handle missing ops. This WAL buffers operations and flushes every 10 ms or every 100 operations, whichever comes first. On recovery, it loads all operations from the database and replays them to reconstruct the document state. This avoids synchronous persistence latency. To scale to millions of documents, shard by document ID. Each shard handles its own operation log and OT logic. Cache the compiled document state in memory, invalidating on new operations. For hot documents, split into sections and shard by section. Each shard manages a set of documents. It caches the compiled state and invalidates on new operations. On cache miss, it rebuilds from the operation log. This keeps reads fast while ensuring consistency. Users expect to edit offline and sync later. The client queues operations locally with a version number. On reconnect, it sends the queue to the server, which transforms each operation against concurrent server operations. Limit queue size to avoid memory pressure. The offline queue stores operations until sync. On sync, it sends the queue with the last known version. The server returns transformed operations that the client applies locally. After successful sync, the queue is cleared. If you need peer-to-peer collaboration without a central server, CRDTs are a better fit. But CRDTs have larger metadata overhead. For server-based editors like Google Docs, OT is simpler and more efficient. In CRDTs, each character has a unique ID and references its predecessors. Operations are commutative, so clients converge without a server. However, metadata grows with tombstones, requiring garbage collection. This is the same issue we highlighted at the start. Here's exactly why that happened. The operation history buffer stored every operation since sessions start without compaction. With 100 users typing at 5 OPSEC, the history grew 500 OPSEC. After 30 minutes, 900K operations consumed 3.6 GB, triggering the OOM killer. The fix was to implement sliding window compaction. Keep only the last 1,000 operations per document in memory, archive older ones to disk with a Bloom filter for conflict checks. Memory dropped from 3.6 GB to 200 MB, and the OOM kills stopped. This is the exact line that caused the OOM incident. Without bounding the history, it grows indefinitely. Always implement a sliding window or compaction strategy to limit memory usage. If your OT functions don't satisfy the transformation properties TP1 and TP2, clients will diverge. Always test with random concurrent operations and verify the final state is identical across clients. Broadcasting cursor position on every mouse move will saturate the network. Throttle to 20 updates per second max, and use a separate low-priority channel so cursor updates don't block document edits. The article's OT code is illustrative. Production systems should use a battle-tested library like Sharding, Node.js, or OTJS. Rolling your own OT is error-prone. Ensure your library supports the same operation types and transformation properties, TP1, TP2, as your application. The article mentions batching operations to reduce overhead. Here's how to transform a batch of operations from one client against the server's history, applying them as a unit to maintain consistency. The article warns about unbounded history causing OOM. In production, implement sliding window compaction. Keep only the last n operations per document, e.g., 1,000, and archive older ones to disk. Use a Bloom filter to quickly check if an archived operation might conflict with a new one, avoiding full replay. To debug issues, first check the operation history, size per document. Profile WebSocket message, size to identify bottlenecks. Use random test harnesses to verify OT functions satisfy TP1, TP2. Monitor memory usage to catch unbounded growth early. Let's run through some common interview questions. How does Google Docs handle concurrent edits? Uses OT with a central sequencer. When to choose CRDTs over OT? For peer-to-peer or offline-first apps. What happens on client reconnect after offline? Server transforms queued ops against history. And a few frequently asked questions. What algorithm does Google Docs use? Operational transformation, OT. How does OT differ from CRDTs? OT needs a server. CRDTs work peer-to-peer. How to handle offline edits? Queue locally, transform on reconnect. To recap, OT needs a central sequencer for total order. Always bound operation history to prevent OOM. Transform cursor positions against operations. And CRDTs are overkill for server-based editors like Google Docs. Ready to go deeper? Up next. Design Instagram, then design a distributed message queue, then design a distributed key-value store. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.